Hello there, and welcome to this peaceful exploration of the nature of reality itself. I'm so glad you've found your way here tonight, ready to contemplate the fundamental nature of existence, the fabric of the universe, and the strange and beautiful truths about the world we inhabit. Wherever you are right now, whatever you're experiencing, I want you to know that you're part of something vast and mysterious, something that has puzzled philosophers and scientists for millennia and continues to reveal its secrets slowly. One discovery at a time, there's something deeply calming about pondering the nature of reality. Perhaps it's the way these big questions put our daily concerns into perspective, reminding us that we're part of something much larger than ourselves. Perhaps it's the realization that reality is far stranger and more wonderful than we usually imagine, that the universe is not just a backdrop for our lives, but an active participant in every moment of existence. Or perhaps it's simply the sense of wonder that comes from learning that the solid, stable world we perceive is actually a shimmering dance of energy, probability, and possibility. Tonight, we're going to journey through the layers of reality, from the quantum realm where particles exist in multiple states at once, to the cosmic scale where space and time themselves bend and warp. We'll explore what physics tells us about the nature of matter and energy, what philosophy reveals about perception and consciousness, and what the intersection of science and contemplation teaches us about being alive in this mysterious universe. If you find peace in these explorations, if contemplating the nature of reality helps you relax and connect with something larger than everyday concerns, consider liking this video and subscribing to the channel. It helps others discover this content too. But for now, just settle in, get comfortable, take a deep breath. You're about to explore the most fundamental questions of existence, and there's nowhere else you need to be. Let's begin our journey into the heart of reality. Everything you see is actually mostly empty space. This might be one of the most counterintuitive facts about reality. When you look around, you see solid objects, walls and furniture, your own body. Everything appears dense and substantial. But at the atomic level, matter is almost entirely empty space. An atom consists of a tiny nucleus surrounded by electrons, and the distance between the nucleus and the electrons relative to their sizes is enormous. If you could expand an atom to the size of a football stadium, the nucleus would be about the size of a pea at the center, and the electrons would be tiny specks orbiting at the outer edges of the stadium. Everything in between would be empty space. This means that you, your body, the chair you're sitting on, the building around you, are all more than 99.9% empty space. The solidity you perceive is actually the result of electromagnetic forces between atoms repelling each other. When you touch something, you're not really touching it in the sense of contact. The electrons in your hand are repelling the electrons in the object, and your brain interprets this repulsion as the sensation of touch. The apparent solidity of matter is an illusion created by forces, not actual physical substance. This realization can be disorienting at first, but there is also something liberating about it. The world is not as fixed and solid as it appears. At the most fundamental level, reality is mostly space, mostly emptiness. Held together by invisible forces in a delicate balance, atoms are ancient, older than the earth and the sun. The atoms that make up your body, that constitute everything you can see and touch, are incredibly old. They were not created when you were born, or even when the earth formed. Most atoms are billions of years old, forged in the hearts of stars long before our solar system existed. The hydrogen atoms in your body, the simplest and most abundant element in the universe, were created in the Big Bang itself, about 13.8 billion years ago. They've existed since the very beginning of the universe. Heavier elements, carbon, nitrogen, oxygen, the building blocks of life, were created inside massive stars through nuclear fusion. When those stars reached the end of their lives and exploded as supernovae, they scattered these elements into space. The atoms then drifted through the cosmos for millions or billions of years, until they became part of the molecular cloud that collapsed to form our sun and solar system about 4.6 billion years ago. The atoms in your body have been on an extraordinary journey. They've been part of stars, part of cosmic clouds, part of the early Earth, part of rocks and oceans, part of ancient organisms, part of the food you ate that became incorporated into your tissues. Every atom has a history stretching back to the birth of the universe. You are, quite literally, made of stardust, a temporary arrangement of ancient matter that will eventually disperse and become part of something else. This continuity, this connection to the deep past and the cosmic future, is a profound truth about your place in reality. Time is not absolute but relative, changing based on speed and gravity. For most of human history, time was thought to be a universal constant, flowing the same for everyone everywhere. But Einstein's theory of relativity revealed that time is actually flexible, malleable, relative. Time passes at different rates depending on how fast you're moving and how strong the gravitational field is around you. If you were to travel in a spaceship at speeds approaching the speed of light, time would slow down for you relative to people on Earth. This is called time dilation. An astronaut traveling at 90% of the speed of light would experience time passing about half as fast as someone on Earth. A journey that felt like 1 year to the astronaut would correspond to more than 2 years passing on Earth. This isn't science fiction. It's been confirmed by experiments with atomic clocks on fast-moving aircraft and satellites. Gravity also affects time. The stronger the gravitational field, the slower time passes. Time moves slightly faster on a mountaintop than in a valley. The difference is tiny, just nanoseconds, but it's real and measurable. GPS satellites have to account for this time dilation to maintain accuracy. Near a black hole, where gravity is extreme, time slows dramatically. An observer watching someone fall toward a black hole would see them slow down, appearing to freeze at the event horizon, while the falling person would experience time normally. This means there's no universal now. Events that are simultaneous for one observer might not be simultaneous for another observer moving at a different speed or in a different gravitational field. Time is not a river that flows the same for everyone, but a personal experience that depends on your motion through space and the gravitational fields you encounter. This relativity of time challenges our intuitive understanding of reality and reveals a universe far stranger than everyday experience suggests. Light has no experience of time. This is one of the most mind-bending implications of relativity. From the perspective of a photon, a particle of light, no time passes at all. Light travels at the speed of light, obviously, and at that speed, time dilation becomes infinite. This means that from light's perspective, if we can call it that, the journey from a distant star to your eye happens instantaneously. A photon emitted from a galaxy billions of light years away experiences no passage of time during its journey. It exists from its frame of reference simultaneously at the moment of emission and the moment of absorption. For the photon, there is no journey, no duration, just an eternal now. This seems impossible to our minds, which are deeply embedded in the flow of time, but it's a consequence of the mathematics of relativity. Light doesn't age. It doesn't experience change. It exists outside of time as we know it. This gives light a kind of immortality, a permanence that contrasts sharply with our ephemeral existence. When you look at the stars, you're seeing light that has traveled for years, centuries, or millennia to reach you. But from the light's perspective, no time has passed. It connects the distant past of the universe directly to your present moment, collapsing vast stretches of time into a single instant. There's something poetic about this, about the timelessness of light, about the way it serves as a bridge across space and time, carrying information from the distant universe to our eyes without ever experiencing the journey itself. Quantum particles can exist in multiple states simultaneously until observed. Welcome to the strange world of quantum mechanics, where reality behaves in ways that defy common sense. At the quantum level, particles don't have definite properties until they're measured. Instead, they exist in a superposition, a state where multiple possibilities coexist simultaneously. The most famous example is Schrödinger's cat. A thought experiment where a cat in a box is simultaneously alive and dead until someone opens the box and observes it. While this sounds absurd, it accurately describes how quantum particles behave. An electron, for instance, doesn't have a definite position until it's measured. Before measurement, it exists as a probability cloud, a spread of potential locations. The electron is, in a sense, in all those locations at once. Only when you measure its position does the probability wave collapse, and the electron appears at a specific point. This isn't just a limitation of our knowledge or measurement tools. The particle genuinely doesn't have a definite state before measurement. It exists in a fuzzy, indefinite state of multiple possibilities. This has been confirmed by countless experiments and is the foundation of quantum mechanics, the most successful theory in physics. But it raises profound questions. What counts as observation? Does it require a conscious observer, or does any interaction with the environment cause the wave function to collapse? How can something exist in multiple states at once? These questions touch on the very nature of reality and remain subjects of debate among physicists and philosophers. Quantum superposition reveals that reality at its most fundamental level is probabilistic, not deterministic, and that the act of observation plays a crucial role in bringing definite reality into existence. Particles can be entangled, connected across any distance instantaneously. Quantum entanglement is perhaps the strangest phenomenon in physics, so strange that Einstein called it spooky action at a distance and refused to believe it was real. But experiments have proven that entanglement is a genuine feature of reality. When two particles become entangled, their properties become correlated in such a way that measuring one particle instantly affects the other, regardless of the distance between them. If you measure the spin of one entangled electron and find it spinning up, the other electron will instantly spin down, even if it's on the other side of the galaxy. This correlation happens faster than light could travel between the particles, seemingly violating the principle that nothing can travel faster than light. But entanglement doesn't actually transmit information faster than light, so it doesn't violate relativity. Instead, it reveals that entangled particles are not truly separate entities, but remain part of a unified system, a single quantum state that transcends space. The connection between entangled particles is not mediated by any signal or force traveling through space. It's a direct connection built into the fabric of reality itself. Entanglement has been demonstrated over distances of hundreds of kilometers and is being used to develop new technologies like quantum computers and quantum communication systems. But beyond its practical applications, entanglement challenges our intuitive notion of locality, the idea that objects are only influenced by their immediate surroundings. In the quantum world, distant objects can be intimately connected, sharing a form of unity that defies spatial separation. This suggests that at a deep level, everything in the universe might be entangled, connected in ways we're only beginning to understand. The observer effect shows that observation changes reality. In quantum mechanics, the act of observation doesn't just reveal information about a system, it fundamentally changes the system. This is called the observer effect, and it's been demonstrated in numerous experiments, most famously the double-slit experiment. When particles, like electrons, are fired at a screen with two slits, they create an interference pattern, alternating bands of light and dark, on a detector behind the slits. This pattern indicates that each electron is behaving like a wave, passing through both slits simultaneously and interfering with itself. But if you place a detector at the slits to observe which slit each electron goes through, the interference pattern disappears. Instead, you get two bands corresponding to particles going through one slit or the other. The act of observation collapses the wave-like behavior into particle-like behavior. The electron, which was in a superposition of going through both slits, is forced into a definite state of going through one slit when observed. This isn't a matter of the observation disturbing the particle mechanically. Even incredibly gentle, non-invasive measurements have the same effect. The issue is that observation itself, gaining information about the system, fundamentally changes the quantum state. This raises profound questions about the nature of reality and consciousness. Does reality only become definite when observed? What constitutes an observer? Is consciousness required, or does any physical interaction count as observation? These questions remain open. But the observer effect demonstrates that we are not passive witnesses to reality, but active participants whose observations help shape what exists. Matter and energy are different forms of the same thing. Einstein's famous equation, E equals mc squared, reveals one of the most fundamental truths about reality. Matter and energy are interconvertible, two manifestations of the same underlying substance. Matter can be converted into energy, as happens in nuclear reactions where a small amount of mass is transformed into enormous amounts of energy. This is the principle behind nuclear power and nuclear weapons, and it's what powers the sun, where hydrogen atoms fuse to form helium, converting some of their mass into the energy that lights our world. Energy can also be converted into matter, though this requires tremendous amounts of energy concentrated in a tiny space. In particle accelerators, when high-energy particles collide, the energy of the collision can create new particles, literally materializing matter from pure energy. This equivalence of matter and energy means that the distinction between them is somewhat arbitrary. What we call matter is really just energy in a stable, localized form. The particles that make up atoms are excitations in quantum fields, little knots of energy vibrating in ways that give them properties like mass and charge. In this view, the universe is not made of stuff, but of energy patterns, waves, and vibrations in underlying fields. Your body, which seems so solid and material, is really a pattern of energy, a temporary configuration that emerged from the quantum fields and will eventually dissolve back into them. This doesn't diminish the reality of your existence, but it does reframe it, suggesting that matter is more like a process, a dynamic pattern, than a static thing. The universe is expanding, and the expansion is accelerating. One of the most profound discoveries of modern cosmology is that the universe is not static, but expanding. Galaxies are moving away from each other, and the space between them is literally growing. This expansion was discovered in the 1920s when astronomer Edwin Hubble observed that distant galaxies show redshift, their light stretched to longer wavelengths by the expansion of space itself. The farther away a galaxy is, the faster it appears to be receding. This led to the conclusion that the universe began in a hot, dense state, the Big Bang, and has been expanding ever since. For decades, astronomers assumed this expansion was slowing down due to gravity. But in the late 1990s, observations of distant supernovae revealed something shocking. The expansion is actually accelerating. Galaxies are not just moving apart, but moving apart faster and faster over time. This acceleration implies the existence of a mysterious force or energy dubbed dark energy that permeates all of space and acts like anti-gravity, pushing things apart. Dark energy makes up about 68% of the total energy content of the universe, yet we have no idea what it is. Its existence is inferred entirely from its effects on cosmic expansion. The accelerating expansion means that the observable universe is getting larger, but it also means that distant galaxies are moving away from us faster than light can travel. Not because they're moving through space faster than light, which relativity forbids, but because the space between us and them is expanding. These galaxies are beyond our cosmic horizon, forever inaccessible to us. The universe is vaster than we can observe, and it's growing larger every moment, carrying parts of itself beyond our reach into a region we can never explore. Most of the universe is made of things we can't see or understand. When astronomers look at the universe, they find that the ordinary matter we're familiar with, the stuff of stars, planets, and people, accounts for only about 5% of the total mass and energy of the universe. The rest is composed of dark matter and dark energy, substances that don't emit, absorb, or reflect light, and are detectable only through their gravitational effects. Dark matter, which makes up about 27% of the universe, acts like an invisible scaffolding that holds galaxies together. Galaxies spin so fast, that the visible matter alone doesn't have enough gravity to keep them from flying apart. Dark matter provides the additional gravity needed to hold them together. It's all around us, passing through the Earth and our bodies constantly, but it interacts so weakly with ordinary matter that we don't notice it. Despite decades of searching, we still don't know what dark matter is made of. The leading candidates are exotic particles that don't interact with light, but none have been directly detected yet. Dark energy is even more mysterious. It's the force driving the accelerating expansion of the universe, a kind of energy inherent to space itself. The more space there is, the more dark energy there is, pushing the expansion to accelerate. We don't know what dark energy is, why it exists, or why it has the strength it does. These unknowns are humbling. After centuries of scientific progress, we've discovered that we understand only a tiny fraction of the universe. The vast majority remains a mystery, a frontier waiting to be explored. This should inspire both humility and wonder, reminding us that reality is far more complex and strange than we yet comprehend. Reality might be a hologram, information encoded on a two-dimensional surface. One of the most radical ideas in modern physics is the holographic principle, which suggests that the three-dimensional universe we experience might actually be encoded on a two-dimensional surface, like a hologram. This idea emerged from studies of black holes. Black holes have an event horizon, a boundary beyond which nothing can escape. Physicists discovered that the maximum amount of information that can be contained within a region of space is proportional to the area of its boundary, not its volume. This is strange because it implies that a three-dimensional volume can be fully described by the information on its two-dimensional surface. Some physicists, including Leonard Susskind and Gerard T. Hooft, propose that this principle might apply to the entire universe. If true, it would mean that everything we experience in three dimensions. All the depth and volume of space is really a projection of information stored on a distant two-dimensional surface, perhaps at the edge of the observable universe. In this view, the three-dimensional world is like a holographic image, a convincing illusion generated from simpler, lower-dimensional data. This doesn't mean the world is fake or illusory in the ordinary sense. It's still real, but its fundamental description might be very different from how we perceive it. The holographic principle has connections to quantum mechanics, information theory, and theories of quantum gravity. It suggests that information is more fundamental than matter or energy, that the universe is at its core an information processing system. While the holographic principle remains theoretical and unproven, it's taken seriously by many physicists and has inspired new ways of thinking about the nature of reality, space, and time. Time might not be fundamental, but an emergent property. We experience time as a fundamental aspect of reality, perhaps the most basic feature of existence. Everything seems to happen in time, one moment following another in an unceasing flow. But some physicists and philosophers argue that time is not fundamental, but emergent, arising from more basic timeless laws. In quantum mechanics and general relativity, time is treated very differently. In relativity, time is part of space-time, a four-dimensional fabric where past, present, and future all exist equally. There's no universal now, no objective flow of time. In quantum mechanics, the equations are often time-symmetric, working equally well forward or backward in time. When physicists try to combine quantum mechanics and general relativity into a theory of quantum gravity, time becomes even more problematic. In some formulations, the fundamental laws are timeless, describing relationships between quantities without reference to time. Time, in this view, emerges from these timeless relationships, much like temperature emerges from the motion of molecules. At the molecular level, there's no such thing as temperature, just particles moving. Temperature is a statistical property of large collections of particles. Similarly, time might be a statistical property, something that emerges when you have a large, complex system, but which doesn't exist at the most fundamental level. This idea is supported by the fact that the arrow of time, the distinction between past and future, seems to be connected to entropy, the measure of disorder. Entropy increases over time, giving time a direction. But at the microscopic level, physical laws are time-symmetric. The arrow of time might emerge from statistical properties rather than being built into the fundamental laws. If time is emergent rather than fundamental, it would be one of the most profound revolutions in our understanding of reality, suggesting that the flow of time is in some sense an illusion, a useful description that emerges at our scale, but doesn't reflect the deepest nature of existence. The laws of physics might be the same everywhere in the universe. One of the fundamental assumptions of modern science is that the laws of physics are universal, the same everywhere and at all times. Gravity works the same on Earth as it does in distant galaxies. Light always travels at the same speed. The properties of electrons are identical, whether they're in your body or in a star billions of light years away. This universality has been confirmed by countless observations. When astronomers look at the light from distant galaxies, they see the same patterns, the same spectral lines from atoms that we observe in laboratories on Earth. This means that atoms and the laws governing them have remained constant for billions of years across vast cosmic distances. This universality is remarkable and not logically necessary. The laws could, in principle, vary from place to place or change over time, but as far as we can tell, they don't. This suggests a deep order to the universe, a consistency that makes science possible. If the laws changed unpredictably, we could never understand or predict anything. The universality of physical laws also implies that discoveries made here on Earth can tell us about the most distant reaches of space and time. We can study the Big Bang, the interiors of stars, the behavior of matter under extreme conditions, all without leaving Earth, because the same laws apply everywhere. This universality gives science its power and suggests that reality, despite its vastness and complexity, is governed by a relatively small set of fundamental principles that we can hope to understand. Constants of nature appear fine-tuned for life. The universe is governed by fundamental constants, numbers that determine the strength of forces, the masses of particles, and other basic properties. These include the speed of light, the gravitational constant, the strength of electromagnetic and nuclear forces, and many others. What's remarkable is that these constants appear to be fine-tuned, set to values that allow for the existence of complex structures like atoms, stars, planets, and life. If many of these constants were even slightly different, the universe would be radically different and likely unable to support life. If the electromagnetic force were slightly stronger or weaker, atoms couldn't form. If gravity were much stronger, stars would burn out too quickly for life to evolve. If it were much weaker, stars wouldn't form at all. The list of such fine-tunings is extensive, and the degree of precision required is often astonishing, like balancing a pencil on its point. This has led to much speculation about why the constants have the values they do. Some argue it's evidence of design, that the universe was created specifically to allow for life. Others point to the anthropic principle, the idea that we can only observe a universe capable of producing observers like us, so it's not surprising that we find ourselves in a life-permitting universe. A third explanation involves the multiverse, the idea that there are many universes with different constants, and we happen to live in one of the rare ones where life is possible. Each of these explanations raises deep philosophical questions about chance, necessity, purpose, and the nature of existence. The fine-tuning of constants remains one of the great mysteries of cosmology, a puzzle that sits at the intersection of physics, philosophy, and perhaps even theology. Reality at the quantum scale is fundamentally probabilistic, not deterministic. Classical physics, the physics of Newton and everyday experience, is deterministic. If you know the current state of a system and the forces acting on it, you can predict its future behavior with certainty. A thrown ball follows a precise trajectory. A planetary orbit can be calculated centuries in advance. But quantum mechanics revealed that this determinism breaks down at the smallest scales. In the quantum world, you can't predict with certainty what will happen, only calculate probabilities. An electron might be here or there, might have this energy or that. You can calculate the odds, but the outcome of any individual measurement is fundamentally random. This isn't because of incomplete information or hidden variables we don't know about. It's an intrinsic feature of quantum reality. Particles don't have definite properties before measurement, only probability distributions. This randomness troubled many physicists, including Einstein, who famously said that God does not play dice with the universe. But decades of experiments have confirmed that quantum randomness is real. Reality is not a clockwork mechanism unfolding according to predetermined laws, but a probabilistic process where multiple outcomes are possible and which one occurs is, at some level, a matter of chance. This has profound implications. It means the future is not entirely determined by the past. There's genuine novelty, genuine openness in the universe. The deterministic worldview, which can feel suffocating, as if everything is predestined, is not true. The universe leaves room for chance, for possibility, for things to be genuinely new and unpredictable. You are made of atoms that were once part of other people, other creatures, other things. The atoms in your body are constantly being exchanged with the environment. You breathe in atoms that were in the air. You eat food containing atoms that become part of your tissues. You shed skin cells and exhale molecules back into the world. Over time, almost every atom in your body is replaced. The atoms you're made of today are not the same atoms that made up your body 7 years ago. This means that the atoms constituting you have been part of countless other structures throughout history. The carbon in your cells was once part of a tree, before that perhaps part of the soil, before that part of another organism, and so on, cycling through the biosphere for billions of years. The water molecules in your body have been through countless other bodies. Human and animal have been parts of rivers and oceans and clouds. The nitrogen in your DNA was part of the atmosphere, was incorporated into plants, was eaten by animals, was returned to the soil over and over. The iron in your blood was forged in a star that exploded before the Earth existed. Every atom has an almost infinitely long history of being part of different structures, playing different roles in different times and places. This means you're not a fixed, isolated entity, but a temporary pattern in a constant flow of matter. You're a wave in the ocean of atoms, a form that arises and persists for a while before dissipating back into the flow. This impermanence might seem sad, but it's also beautiful. It connects you to everything else, shows that you're part of a larger whole, that the boundary between self and world is fluid and porous, not fixed and absolute. Space and time are not separate, but form a unified space-time. Before Einstein, space and time were thought of as separate, absolute entities. Space was the stage on which events occurred, and time was the universal clock, marking their progression. But Einstein's theory of relativity showed that space and time are intimately connected, forming a single four-dimensional entity called space-time. Events don't happen in space at a certain time. They happen at specific points in space-time. The separation of space-time into space and time is relative, depending on your motion. What one observer considers space and time, another moving observer divides up differently. Moreover, space-time is not a passive stage, but an active participant in physics. Mass and energy curve space-time, and this curvature is what we experience as gravity. The Earth orbits the Sun not because of a force pulling it, but because the Sun's mass curves space-time around it, and the Earth follows a straight path through this curved geometry. Similarly, time is affected by gravity, passing more slowly near massive objects. Near a black hole, space-time is so warped that time nearly stops, and space is stretched and compressed in extreme ways. The fabric of space-time can ripple, creating gravitational waves that propagate across the universe at the speed of light. These waves have been detected, confirming Einstein's predictions. Understanding space-time requires letting go of intuitions built from everyday experience and embracing a more unified, geometric view of reality where space and time are aspects of a single, flexible structure shaped by matter and energy. Black holes are regions where space-time curvature becomes infinite. Black holes are among the most extreme and mysterious objects in the universe. They form When a massive star collapses at the end of its life, compressing so much mass into such a small volume that the gravitational field becomes overwhelming. At a certain radius, called the event horizon, the escape velocity exceeds the speed of light. Nothing, not even light, can escape from inside the event horizon. To an outside observer, a black hole appears as a dark region in space, defined by its event horizon. But the true weirdness lies at the center, where all the mass has collapsed to a point of infinite density called a singularity. At the singularity, space-time curvature becomes infinite, and our current theories break down. We don't know what actually happens there. General relativity predicts a singularity, but most physicists believe that a theory of quantum gravity would resolve the infinity, showing what really occurs in the black hole's core. Black holes also have strange effects on time. As you approach a black hole, time slows down relative to observers far away. At the event horizon, time dilation becomes infinite. To an outside observer, anyone falling into a black hole appears to slow down and freeze at the horizon, never quite crossing it. But to the falling person, time passes normally, and they cross the horizon in finite time, experiencing nothing special at that point, then continue falling toward the singularity. Black holes are not cosmic vacuum cleaners, sucking everything in. They exert gravity just like any other mass. If the sun were replaced by a black hole of equal mass, Earth would continue to orbit normally, just without sunlight. Black holes can also evaporate, slowly emitting Hawking radiation, a quantum effect predicted by Stephen Hawking. Over incredibly long timescales, black holes radiate away their mass and eventually disappear. Though for large black holes, this process takes far longer than the current age of the universe. The universe may have no edge and no center. When we think about the universe, we often imagine it as a vast expanse with boundaries and a center, perhaps expanding outward from the point where the Big Bang occurred. But this picture is misleading. The Big Bang was not an explosion in a pre-existing space, but the emergence of space itself. Every point in the universe was at the location of the Big Bang, because space has expanded from every point. There's no center of the expansion. Every galaxy sees all other galaxies moving away from it. This is possible because the universe's geometry might be different from our intuitive expectations. If the universe is infinite, it has no edge or center. But even if it's finite, it might have no boundary. One possibility is that the universe has a closed geometry, like the surface of a sphere. A sphere's surface is finite in area, but has no edge or boundary. No matter where you go on a sphere's surface, you never reach an end. You just eventually come back to where you started. The universe's three-dimensional space might curve back on itself in a similar way, forming a closed shape with no boundary. In such a universe, you could travel in a straight line in any direction and eventually return to your starting point. Another possibility is that the universe is flat or open but infinite in extent, stretching on forever in all directions. Current observations suggest the universe is very close to flat on large scales, which is consistent with being infinite. The question of the universe's shape and whether it's finite or infinite remains open, but either way, the universe likely has no center, no preferred location. Every place is as good as any other, a principle called the cosmological principle, which underlies much of modern cosmology. You are observing the past whenever you look at anything. Light takes time to travel, and this creates a fundamental limitation on how we perceive reality. When you look at the sun, you're seeing it as it was about 8 minutes ago, the time it takes light to travel from the sun to Earth. When you look at the nearest star system, Alpha Centauri, you're seeing it as it was about 4 years ago. When you look at distant galaxies through a telescope, you're seeing them as they were millions or billions of years ago. The most distant objects we can see, radiation from the early universe, show us the cosmos as it was nearly 14 billion years ago, just hundreds of thousands of years after the Big Bang. This time delay means we can never see the universe as it is now, but only as it was. We're always looking into the past. Even on smaller scales, there's a delay. When you look at a person across the room, You're seeing them as they were a few nanoseconds ago, the time it took light to travel from them to your eyes. Your entire perception of the world is slightly out of date, a reconstruction of the past. Your brain processes sensory information with additional delays, so the conscious experience you're having right now actually corresponds to events that occurred fractions of a second ago. We live perpetually in the past, perceiving a reality that no longer exists, constructing a continuous experience from delayed information. This doesn't diminish the validity of our perceptions, but it reveals that our experience of the present is actually a sophisticated illusion, a model built from past data. The Big Bang was not an explosion in space, but an expansion of space itself. The term Big Bang is somewhat misleading because it conjures images of an explosion, matter flying outward from a central point into pre-existing empty space. But the Big Bang was nothing like that. It was the beginning of space and time themselves. Before the Big Bang, there was no space, no time, no before. The universe didn't expand into something. Space itself expanded, carrying matter and energy along with it. In the earliest moments after the Big Bang, the universe was incredibly hot and dense, but it was everywhere at once, not concentrated at a single point. Every point in space was part of the initial hot, dense state. As the universe expanded, space stretched, and the density and temperature decreased. This expansion continues today, with galaxies moving apart as the space between them grows. It's crucial to understand that galaxies aren't moving through space away from each other. The space itself is expanding, carrying galaxies with it. This is why distant galaxies can be receding faster than light without violating relativity. They're not moving through space faster than light. Space itself is expanding faster than light between us and them. The Big Bang also marked the beginning of time. Asking what happened before the Big Bang might be a meaningless question, like asking what's north of the North Pole. If time itself began with the Big Bang, there was no before. This is a strange and difficult concept to grasp, but it's the current scientific understanding. The Big Bang is not an event that occurred in time, but the event that created time, space, matter, and energy, the origin of everything we can observe or measure. Reality might not be objective, but depends on the observer. One of the most unsettling implications of quantum mechanics is that reality might not have objective properties independent of observation. In the classical worldview, objects have definite properties whether anyone is looking or not. A tree falling in an empty forest makes a sound even if no one is there to hear it. But quantum mechanics suggests this might not be true at the smallest scales. Particles don't have definite positions, velocities, or spins until they're measured. Before measurement, they exist in superpositions of multiple states. The act of observation collapses the superposition, forcing the particle into a definite state. But different observers might make different measurements and collapse the wave function in different ways, leading to different realities. This has led some physicists to propose interpretations of quantum mechanics where reality is observer-dependent. In the relational interpretation, quantum states are not absolute, but relative to the observer. Two observers might describe the same system using different quantum states, and both descriptions are equally valid. In some interpretations, such as the many worlds interpretation, every possible outcome of a quantum measurement actually occurs, but in different branches of reality. When you measure a particle's spin, the universe splits into branches where you observed spin up and spin down, and both versions of you exist in parallel realities, each experiencing a different outcome. While these interpretations remain controversial and philosophical rather than experimentally testable, they highlight a profound shift from classical thinking. Reality might not be a single objective state of affairs that exists independently of observers, but something more fluid, more dependent on perspective, more intimately connected to the act of observation itself. This doesn't mean reality is arbitrary or that you can change things just by thinking about them. The rules of quantum mechanics are precise and predictive, but it does suggest that the relationship between observer and observed is more complex than we once thought. That consciousness and measurement play roles we're still trying to understand, and that the objective, observer-independent reality we take for granted might be an approximation that breaks down at the quantum level. Everything in the universe is connected through quantum entanglements past. While quantum entanglement between specific particles requires them to have interacted in specific ways, there's a deeper sense in which everything in the universe might be connected. In the early moments after the Big Bang, when the entire observable universe was compressed into a space smaller than an atom, all the particles and energy that would eventually become stars, galaxies, planets, and people were in intimate contact. They were part of a single, unified quantum system. As the universe expanded and cooled, this system became vastly more complex and separated, but some physicists argue that the original entanglement might never be completely lost. If true, this would mean that everything in the universe retains some quantum connection to everything else, an invisible web of correlations linking all matter and energy. This idea resonates with ancient philosophical and spiritual traditions that speak of the fundamental unity of all things, the interconnectedness of existence. While the practical implications of such universal entanglement would be impossible to detect or exploit, given the decoherence and environmental noise that destroy quantum coherations in complex systems, the conceptual implication is profound. It suggests that separation is, in some sense, an illusion, that at the deepest level, everything that exists is part of a single unified whole. The boundaries we perceive between objects, between ourselves and the world, are real and important at our scale, but they might not reflect the fundamental nature of reality, which is more interconnected, more holistic than our everyday experience suggests. The universe might be one of many in a vast multiverse. The idea of a multiverse, that our universe is just one of many, perhaps infinitely many universes, has moved from science fiction to serious scientific consideration. Several lines of reasoning suggest the possibility of multiple universes. In eternal inflation theory, the rapid expansion called inflation that occurred in the early universe might not have happened just once, but continues to happen in different regions of space, with each region spawning new universes with potentially different physical properties. In the many worlds interpretation of quantum mechanics, every quantum measurement creates new branches of reality, effectively creating countless parallel universes where every possible outcome occurs. String theory, which attempts to unify quantum mechanics and gravity, suggests there might be many different ways to configure the extra dimensions the theory requires, each configuration corresponding to a different universe with different physical laws and constants. If the multiverse exists, it would have profound implications. It could explain the fine-tuning of constants in our universe. If there are infinitely many universes with different constants, it's not surprising that we find ourselves in one of the rare ones that permits life. It would also mean that the universe we observe, vast as it is just a tiny fragment of total reality. Most of the multiverse would be forever beyond our reach, causally disconnected from us, unobservable in principle. This raises philosophical questions about what science can and should address. If other universes are unobservable, can we meaningfully say they exist? Or does science require that theoretical entities be observable, at least in principle? The multiverse remains speculative, but it's taken seriously by many cosmologists and represents one possible future direction for our understanding of reality. The direction of time might be an illusion created by increasing entropy. Why does time flow in one direction from past to future? Why do we remember the past, but not the future? Why can we influence the future, but not the past? These questions relate to what's called the arrow of time, the asymmetry that distinguishes past from future. Surprisingly, most fundamental laws of physics are time-symmetric. If you reverse time in the equations, they still work. A film of microscopic particles bouncing around could be run forward or backward, and you couldn't tell the difference. Both directions obey the same laws. But in our everyday experience, time clearly has a direction. Eggs break but don't spontaneously reassemble. People age but don't get younger. Heat flows from hot to cold, not the reverse. This directionality comes from the second law of thermodynamics, which states that entropy, roughly speaking, disorder, or the number of possible microscopic states, always increases in isolated systems. The arrow of time points in the direction of increasing entropy. But why did entropy start low? The early universe, just after the Big Bang, was in a state of extremely low entropy, highly ordered. As the universe expanded, entropy increased, and it continues to increase today. The low entropy initial condition is what gives time its direction. If the universe had started in a high entropy state, there would be no arrow of time, no distinction between past and future. Some physicists argue that the perception of time flowing is an illusion created by this entropy increase. At the fundamental level, all moments of time exist equally in the space-time structure. Past, present, and future are all equally real. But we experience time as flowing because our memories, our sense of causation, our very consciousness all depend on entropy increasing. We remember the low entropy past but not the high entropy future because memory formation is an entropy increasing process. The flow of time might be something our minds impose on reality, a feature of how we process information, rather than something fundamental to the universe itself. Consciousness might be the most mysterious phenomenon in existence. Consciousness, the subjective experience of being aware, of having sensations, thoughts, and feelings, is in many ways the most puzzling aspect of reality. We know that consciousness exists because we experience it directly. But how physical processes in the brain give rise to subjective experience remains deeply mysterious. This is called the hard problem of consciousness. We can explain, at least in principle, how the brain processes information, how it responds to stimuli, how it controls behavior. These are problems of neuroscience and cognitive science. But explaining why these processes feel like something, why there's an inner experience accompanying them, seems to require something more. Why is there something it's like to see red, to feel pain, to taste chocolate? Why aren't we just unconscious automata, processing information without any inner light of awareness? Some philosophers and scientists argue that consciousness is fundamental, not reducible to physical processes. In this view, consciousness might be a basic feature of reality, like space, time, or matter. Others believe consciousness will eventually be explained by neuroscience and physics once we understand the brain's complexity more fully. Still others propose that consciousness is an illusion, that the sense of a unified continuous self is a story the brain tells, a useful fiction, but not something that exists as we experience it. These questions touch on the deepest issues in philosophy and science: the nature of mind, the relationship between subjective and objective, the place of consciousness in the physical world. Consciousness is the lens through which you experience everything else. Yet it remains largely opaque to itself, a mystery at the very center of your being. Every moment of your life exists eternally in space-time. In Einstein's four-dimensional space-time, the past, present, and future all exist equally. There is no objective now that sweeps through time, turning future into past. Instead, all moments are equally real, laid out in the four-dimensional structure like frames in a film. Your birth, your childhood, this present moment, your future old age, all exist as events in space-time, each with specific coordinates. This view, called the block universe or eternalism, suggests that nothing truly passes away. Every moment you've lived continues to exist in its place in space-time. Every joy, every sorrow, every mundane moment is preserved eternally as part of the space-time fabric. You, as a four-dimensional object, stretch from your birth to your death, a long continuous thread through space-time. At each moment, you experience only a three-dimensional slice, the present, but all the slices exist together in the full structure. This view can be comforting and disturbing. Comforting because nothing is truly lost. Every beautiful moment exists forever. Disturbing because it suggests a kind of determinism, that the future already exists, laid out in space-time, waiting for your consciousness to reach it. But some physicists argue against the block universe, suggesting that the future might not be determined, that space-time is not static but growing, with new moments coming into being. The tension between these views reflects deep questions about time, free will, and the nature of becoming, regardless of which view is correct. The block universe perspective invites you to see your life not as a series of fleeting moments, but as a complete four-dimensional structure, a trajectory through space-time that has its own shape and beauty when viewed as a whole. You are made of the same substance as stars. This is not metaphor but literal truth. The atoms that make up your body, the carbon, nitrogen, oxygen, and other heavy elements, were created inside stars through nuclear fusion. Hydrogen atoms forged in the Big Bang fused to form helium in the cores of stars. In more massive stars, helium fused to create carbon and oxygen. In the final stages of massive stars' lives, even heavier elements formed: nitrogen, phosphorus, sulfur, iron. When these massive stars exploded as supernovae, they scattered these elements into space. The atoms then became part of molecular clouds, vast regions of gas and dust drifting through the galaxy. Eventually, gravity pulled some of this material together to form a new star, our Sun, and the planets around it, including Earth. The atoms in your body were once inside a star, subjected to temperatures of millions of degrees, fused from lighter elements in nuclear reactions. They were then expelled into space, drifted for millions of years, became part of the Earth, were cycled through rocks and oceans and living things, and finally, through the food you eat and the air you breathe, became part of you. You are made of stardust, quite literally. The connection is not just poetic but physical and direct. The matter of your body has a cosmic origin and a cosmic future. When you die, the atoms will return to the Earth, will eventually be recycled, might one day be part of other stars. You are a temporary arrangement of matter that has existed since the beginning of the universe, and will continue to exist long after you're gone, constantly changing form, but never truly created or destroyed. The universe appears to be fine-tuned not just for life, but for complexity. Beyond the fine-tuning that permits atoms and stars, there's another level of fine-tuning that allows for complex structures. Complexity requires a balance between order and chaos, between forces that try to make everything uniform, and forces that create and maintain differences. If the universe were too orderly, it would be static, unchanging, with no room for interesting structures to form. If it were too chaotic, structures would form, but immediately fall apart. The universe seems to sit in a narrow band where complexity is possible. Stars can form but don't immediately collapse or explode. Galaxies can form and maintain their structure for billions of years. Planets can exist in stable orbits. Chemical reactions can occur without everything dissolving into equilibrium. Life can emerge and evolve. This balance is precarious and depends on many factors: the strength of fundamental forces, the masses of particles, the initial conditions of the universe. A slightly different universe might be lifeless, not because atoms couldn't form, but because it would be too simple, too uniform, lacking the richness needed for interesting phenomena. This fine-tuning for complexity is even more striking than fine-tuning for life alone. It suggests that the universe is, in some sense, generative, creative, capable of producing novelty and complexity. Whether this is by design, by chance, or by some principle we don't yet understand remains one of the deepest questions in cosmology and philosophy. Reality might be fundamentally made of information, not matter or energy. In recent decades, some physicists have proposed that information is the most fundamental constituent of reality, more basic than matter or energy. This idea has roots in several areas of physics. Black hole thermodynamics revealed that the entropy of a black hole, a measure of its information content, is proportional to the area of its event horizon, suggesting a deep connection between information and space-time. Quantum mechanics is fundamentally about information, with measurements yielding bits of information, and quantum states being describable in terms of how much information they contain. The holographic principle suggests that the information content of a volume of space is encoded on its boundary, hinting that information is more fundamental than three-dimensional space itself. Some physicists, like John Wheeler, propose that the universe is fundamentally participatory, that information and observers play a constitutive role in bringing reality into being. Wheeler coined the phrase "it from bit," suggesting that every physical quantity, every it, derives its existence from observations and answers to yes or no questions, from bits of information. If reality is fundamentally informational, it would mean that the universe is more like a computational process than a mechanical system, more like a simulation running on some underlying substrate than a collection of material objects. This doesn't mean the universe is a simulation created by someone. It means that at the deepest level, physical processes might be best described as information processing. Matter and energy would be emergent properties, patterns in information flow. This perspective is still speculative and controversial, but it represents a radical reimagining of what reality fundamentally is. The present moment is all that ever exists. While physics describes time as a dimension and the block universe suggests all moments exist equally, there's another perspective worth considering: presentism, the view that only the present moment exists. The past no longer exists. It's gone, preserved only in records and memories. The future doesn't yet exist. It's pure potential, not yet realized. Only now is real. This view aligns with certain interpretations of quantum mechanics, where the future is genuinely open, not determined, and the past, once observed, becomes fixed, but no longer exists as a physical reality. Presentism also resonates with direct experience. You never experience the past or future. You only ever experience now. The past is a memory, a mental construct. The future is an anticipation, a projection. The present moment is the only time you ever actually inhabit. If only the present exists, it makes the now infinitely precious. This moment is not just a point along a timeline, but the entirety of existence, all that is real. The past has released you, and the future hasn't claimed you yet. You exist in an eternal now, a constantly refreshing present that is the arena of all experience and all possibility. This perspective can be grounding, calling attention away from regrets about the past or anxieties about the future, and focusing awareness on the only thing that's actually real, this present moment. With all its sensations, thoughts, and possibilities, you are an arrangement of particles that became aware of itself. One of the most astonishing facts about reality is that matter arranged in certain ways becomes conscious. The universe spent billions of years assembling atoms into stars, then planets, then molecules, then living cells, then complex organisms with nervous systems, and eventually brains capable of consciousness. You are a collection of atoms, the same kinds of atoms that make up rocks and stars and oceans, but organized in such a specific, intricate way that you have subjective experiences, thoughts, feelings, the sense of being someone. The universe, through you, has become aware of itself. You are a way the universe observes itself, contemplates itself, asks questions about itself. Atoms forged in stars have organized into a structure that can understand stars. Matter has become aware of matter. The implications are profound. Consciousness is not something separate from the physical world, not a ghost in a machine, but a property that emerges from matter organized in particular ways. You are entirely physical, entirely part of nature, yet you have this inner light of awareness that feels fundamentally different from mere matter. This emergence of consciousness from matter is one of the great mysteries, but it's also a beautiful truth. It means the universe is not dead, not meaningless. It can generate life, awareness, meaning. Through consciousness, the universe explores possibilities, appreciates beauty, creates art, and science and love. You are that process happening, a localized region of complexity, where the universe has learned to know itself. The vacuum of space is not empty, but full of energy. When we think of empty space, we imagine nothing, a void devoid of matter and energy. But quantum mechanics reveals that even the emptiest space possible is not truly empty. Due to the uncertainty principle, Quantum fields are never completely still. They fluctuate constantly, with virtual particles popping into and out of existence, borrowing energy from the vacuum for infinitesimally brief moments before annihilating. These vacuum fluctuations have measurable effects. They cause the Casimir effect, where two metal plates placed very close together in vacuum are pushed together by the difference in vacuum energy between the plates and outside them. They contribute to the Lamb shift in hydrogen atoms. They're part of Hawking radiation from black holes. The vacuum has energy called zero-point energy or vacuum energy. This energy might be related to dark energy, the mysterious force driving the accelerating expansion of the universe. If so, then the vacuum of space itself is pushing the universe apart, and its energy density determines the ultimate fate of the cosmos. The fact that empty space has energy challenges our intuition. It suggests that nothingness is not a state of affairs that can exist, that there's no such thing as absolute nothing. Even in the absence of matter and radiation, space itself is dynamic, filled with activity at the quantum level. This gives nothing a kind of richness, a potential for creating something from what appears to be nothing. Reality might have more dimensions than we can perceive. We experience 3 dimensions of space and 1 of time, but several theories in physics suggest there might be additional dimensions. String theory, which attempts to unify all forces and particles, requires extra spatial dimensions to be mathematically consistent, typically 6 or 7 additional dimensions beyond the familiar 3. These extra dimensions are thought to be compactified, curled up so tightly that they're invisible at everyday scales. Imagine an ant walking on a tightrope. From far away, the rope looks one-dimensional, a line. But up close, the rope has thickness, a tiny circular dimension wrapped around the line. If the rope's thickness is small enough, the ant might explore the circular dimension while appearing to move only along the line. Similarly, we might be moving through extra dimensions without noticing because they're compactified at scales far smaller than an atom. These extra dimensions would affect physics in subtle ways, potentially explaining the hierarchy of forces and particle masses. Other theories, like brain world scenarios, suggest we might live on a 3-dimensional membrane embedded in a higher dimensional space, like a sheet of paper floating in a room. Gravity might propagate through the extra dimensions while other forces are confined to our brain. If extra dimensions exist, they would fundamentally change our understanding of space. What we think of as the full extent of space would be just a slice through a higher dimensional reality. This possibility is humbling, suggesting that our perception captures only a tiny aspect of the full structure of the universe. The universe is governed by symmetries that shape physical laws. Symmetries, transformations that leave something unchanged, are central to modern physics. A sphere looks the same when rotated. It has rotational symmetry. Physical laws have symmetries too, and these symmetries are deeply connected to conservation laws through Noether's theorem, one of the most beautiful results in theoretical physics. The fact that physical laws are the same at all times leads to the conservation of energy. The fact that they're the same at all places leads to the conservation of momentum. The fact that they're the same in all directions leads to the conservation of angular momentum. More abstract symmetries lead to conservation of quantities like electric charge. Symmetries also guide the search for new physics. When physicists build theories, they often start with symmetries, asking what laws would respect certain symmetry principles. The standard model of particle physics is built on symmetries. Einstein's general relativity is based on a symmetry principle, that the laws of physics should be the same in all reference frames. The deep role of symmetry in physics suggests that reality has an underlying order, a structure that constrains what's possible. The universe is not arbitrary but follows patterns, and these patterns are mathematical, expressible as symmetries. This mathematical structure gives the universe a kind of elegance, a beauty that physicists often talk about, and that guides their intuition toward true theories. And now, as we approach the end of our journey through the nature of reality, let yourself rest in the wonder of existence. We've explored the structure of matter, the nature of space and time, the quantum world's strange properties, the cosmic scales of the universe, and the deep questions about consciousness, observation, and the fundamental fabric of all that is. Reality, as we've discovered, is far stranger and more beautiful than everyday perception reveals. The solid world is mostly empty space. Time is relative, flexible, perhaps even emergent rather than fundamental. Particles exist in multiple states until observed. The universe is expanding, carrying galaxies away from each other in an accelerating cosmic dance. Most of the universe is made of dark matter and dark energy we don't understand. Consciousness arises from matter organized in intricate ways, and through consciousness, the universe observes itself. These facts might seem abstract or distant from daily life, but they're the deepest truths we know about the world you inhabit. Every breath you take involves atoms billions of years old. Every moment you experience exists in the eternal structure of space-time. Every observation you make participates in the quantum process that brings definite reality into being. You are made of stardust, animated by the same laws that govern galaxies, connected through quantum entanglement's historical web to everything that exists. Understanding reality at this level can be both humbling and empowering. Humbling because it reveals how much we don't know, how much mystery remains, how small we are in the cosmic scheme. But also empowering because it shows we're part of something magnificent, something that has been unfolding for billions of years and will continue for billions more. You're not separate from reality, but an integral part of it. A way reality experiences itself. As you drift toward sleep tonight, know that you're floating in a universe more strange and wonderful than anything imagination alone could conceive. The fabric of reality supports you, the laws of physics enable your existence, and the flow of entropy gives time its direction, allowing you to experience this moment, these thoughts, this gentle descent into rest. Thank you for exploring the nature of reality with me tonight. May your dreams be as mysterious and beautiful as the quantum realm, as vast as cosmic space, as timeless as the eternal now. Sleep well, knowing you're made of stars, connected to everything, and participating in the grand unfolding of existence itself. Good night, dear traveler through space-time. May you rest peacefully in the wonder of simply being.